Hello everyone. So today's topic is enzyme kinetics. In this online lecture, we are going to learn about few key points of enzyme kinetics. So these are the three important key points of enzyme kinetics that we are going to learn today. The first key point here is the derivation of Michaelis Menten's equation from the assumptions. And the second point, observations from Michaelis Menten's plot, Km and Kcat values for different enzymes. The third point here is the creation of Lineweaver-burk plot, an explanation of enzyme inhibition by Lineweaver-burk plots. So before going to the main topic, so we need to learn about one important theory, that is law of mass action. According to the law of mass action, here the rate of reaction, so which is proportional to the product of active masses of reacting substances. So here, in this law of mass action, will be explaining about the equilibrium reaction. Here, so A plus B, so which are reactants, which are reacting together and forming C and D. So which is a forward reaction. In the backward reaction, C and D, so which are reacting each other and forming A and B. Here, this is the equilibrium reaction, so which is having forward reaction and backward reaction. Here, forward reaction, which is we are mentioning here with K prime, and backward reaction, which is denoted by K double prime. So at equilibrium reaction, the forward reaction which is equals to the backward reaction. So here the rate of reaction of forward reaction which is equals to K prime into A concentration into B concentration. The rate of reaction of the backward reaction which is equals to K double prime into C concentration into D concentration. Here finally, so from this equilibrium reaction, so we can write the rate of equilibrium reaction which is equals to equilibrium constant K into A concentration into B concentration upon C concentration and D concentration. So in this way, so we can write the rate of reaction, so by using law of mass action. So this is about the law of mass action, and this concept is essential to understand the enzyme kinetics. So here in this slide, so we are going to learn about the derivation of Michaelis Menten's equation. So this equation is very essential for explaining about the relationship between substrate concentration and also the velocity of enzyme reaction. Here, so this is the substrate, so which is reacting with the enzyme and forming enzyme substrate complex at a transition state. So this is the forward reaction K1. The enzyme substrate complex will be going back and forming enzyme and substrate, and this is a backward reaction, so which is denoted by K minus 1. Here, enzyme substrate is not not a product, so which is converting into product here by the reaction of K2. But here K2 minus reaction that we are ignoring here. So why? Because if you are comparing with the concentrations of products with enzyme substrate complex, here the product concentration will be low. So that's why, so it is highly impossible to convert the products into enzyme substrate complex. So that is why, so we are ignoring K minus 2 reaction. So that means here we are having only two forward reaction, that is K1 and K2, and one backward reaction, that is K minus 1. In the first step, we are taking a rapid equilibrium reaction between ES and ES complex. So that means here the forward reaction K1, so which is equal to the backward reaction K minus 1. So according to the law of mass action, here K1, which is multiplied with active mass of E into active mass of S, so which is equals to a backward reaction, that is K minus 1, so which is depending upon the active mass of enzyme substrate complex. So from this equation, so we can take the ratio of K minus 1 by K1, so which is called to be Km, so which is a Michaelis Menten constant, so which is equals to E into S divided by ES concentration. But here, so this equation will be coming from the equilibrium reaction, that is K1 and K minus 1. But here, this enzyme is not the total enzyme. So here we are converting this enzyme portion into total enzyme in the next step. So in this step here, E, so which is equals to E naught. So E naught is a overall enzyme concentration or total enzyme concentration present in the catalysis process, minus ES, so enzyme substrate complex. So that means, so here the E which is giving, so E naught value minus ES. So this value that we are substituting at this position. So before substituting the value at E position, here we have to rearrange the equilibrium constant. So that means here Km values we are keeping here at a denominator, and we are taking ES values at here. So finally here we can get ES, so which is equals to E into S divided by Km. Now this E value will be substituted by, so this value, that is E naught minus ES. So this is the value, so which is obtained from the equilibrium reaction. Here we are simplifying this equation in the next step. Here Km value, so which is multiplying with ES and forming ES into Km, so which is equals to E naught is multiplied with S, E naught S, minus ES is multiplied with S, ES into S. But here in this equation, the negative sign component, so which will be coming to the left hand side, and now we can write it as ES into Km plus ES into S, which is equals to E naught into S. Here ES portion will be common in these two components, so that's why, so we are taking it as common. So ES in brackets Km plus S, so which is equals to E naught into S. So from this equation we are extracting ES values, that is ES equal to E naught into S upon Km plus S. So this equation is also coming from the equilibrium reaction. So now we are linking this equation with the product equation, so that we are learning in the next step. So this is the K2 reaction. So that means the rate of product formation V can be expressed in terms of S. So that means the K2 value, the K2 reaction, which is multiplied with ES, which will be giving V. So V is a rate of reaction, so which is equals to dP by dt. So dP means here change in products with respect to time. If more products are obtained with respect to time, so that means the more velocity of reaction will be present. So here V is finally equals to K2 into ES. So according to the law of mass action. So why? Because K2 is depending upon the concentration, that is ES complex. Now ES value that we are substituting here with the previous value that we got already. So this is the ES value. So here this value that we are substituting here and forming this equation, K2 into E naught into S divided by Km plus S. Here K2 into E naught value, we can take it as V max. So V max is the maximum rate of reaction when the enzyme is saturated with substrate, into S. So S is substrate upon Km, Michaelis Menten constant, plus substrate constant. So this is about the equation of Michaelis Menten's approach, so which will be derived from the few important assumptions. In the next slide, so we are going to learn about So those assumptions, so which from which so Michaelis Mentence derived this equation. So these are the four important assumptions that Michaelis and Menten so derived the equation, the final equation. The first assumption is the binding of E and S is reversible. So that means here enzyme is reacting with substrate and forming enzyme substrate complex, so which is an equilibrium reaction, which is a reversible reaction. And here enzyme substrate is not a stable form, so it is again converting back to enzyme and substrate. So this is the first assumption of Michaelis Menten. And the second assumption here is the product formation K2 step, so which is a rate limiting step. Here the K2 step, which is a forward reaction for converting ES complex into products, that is E plus P. But here the K2 is not a reversible reaction. So why? Because that we have already discussed that K minus 2 is negligible or ignored. So why? Because here products concentration is very less. So these products cannot be converting into ES complex. So that's why we are ignoring K minus 2 reaction. So here the K2 step is a rate limiting step. So that means the K2 step is depending upon only one concentration, that is ES. So enzyme substrate complex. So this is about the second assumption. And the third assumption here is a steady state assumptions. And here ES complex is acting as a constant. So here ES is acting as a constant. So why? Because here ES can form quickly, as well as it can break down into products and substrates quickly. So this is the fourth assumption of steady state assumptions, that ES forms as quickly as it breaks down. So ES can be forming easily, so by K1 reaction, that is a forward reaction, and ES can be break down into products by K2 reaction, and also ES can be converting back to E and ES in K minus 1 reaction. And the next assumption, so K1 step is very fast. So here we are having three important steps, K1, K2 and K minus 1. Here K1 is a forward reaction, so which is very quickly occurring. So when it is comparing with K2 and K minus 1. So this is the second assumption. And the third one is the substrate concentration will be more than enzyme concentration. So this is one of the important assumptions. So here's enzyme concentration will be less, the substrate concentration will be more. So that's why the formation of ES complex will be depending upon the minimum amount of the concentration which is acting in the reactants. If enzyme concentration increases, so ES concentration also will be increases. So that's why here enzyme concentration will be less than substrate concentration. So that is why in the Michaelis Maintenance plot, so we are getting a Vmax value, so which is almost stable. So we can know that observation in the next slide. And the fourth assumption here is the initial velocity assumptions. That is, we are ignoring K minus 2 value. So why? Because K minus 2, which is a backward reaction, so which is useful for converting products into ES complex. Here, so this reaction is completely ignored. So why? Because the concentration of products are comparatively less. So that's why there is no favorable reaction. There is no favorable backward reaction is occurring here. So that's why we are ignoring K minus 2 reaction. So this is the fourth assumption of Michaelis Mentence. So this is a Michaelis Mentence plot. Here on x-axis we are taking substrate concentration S. On y-axis we are taking initial reaction rate, that is V. So here we have to learn two important terms, that is Vmax value. So this is the Vmax value. So which is defined as the maximum rate of reaction when enzyme is saturated with substrate. And here also we are learning Km value. So what is Km value? The Km value is the concentration of substrate which permits the enzyme to achieve half Vmax value. So at half Vmax value, so it is giving Km value, so which is also one of the type of substrate. So this Km value and this Vm values so will be acting like as qualitative parameters. So that means so different enzymes, so different inhibitors and different activators are having different Km values. Here we are getting hyperbolic equation. So up to this level, here linearity we can achieve, but after that level here, so we are getting a stable line. So here the Vmax is giving this value, but here it is not completely stable. So slightly it is increasing. So this is a hyperbolic plot that we are getting in Michaelis Menten's plot. So here we can see inhibitors plot as well as activators plot. So this is the normal Michaelis Menten's plot for the enzymes. So this is inhibitors and here this is activators. So the addition of activators, so shift the graph to the left hand side, and addition of inhibitors will shift the graph to the right hand side. So from this normal graph, so we can easily identify the inhibitors and allosteric activators of that particular enzyme. And this plot, this table is very much important. So here, so we are having different enzymes and their Km values and Kcat values. So Km values is the minimum effective concentration, so which is required to form a product. So that means the carbonic anhydrase, which is an enzyme, so which is forming a complex, with substrate, that is carbon dioxide. Here the carbon dioxide minimum effective concentration must be 8,000 millimoles. So if it is forming 7,500 millimoles, that means it cannot produce any products less than Km values. So this is the minimum value it requires to form a products. And here the Kcat value, so which is also called to be turnover number. So here that turnover number, so which is means that the carbonic anhydrase enzyme, so will be catalyzing the substrate molecules per every second. For example, here carbonic anhydrase enzyme, so will be catalyzing 6 lakh substrate molecules for every 1 second. So this is about turnover number of carbonic anhydrase. And chymotrypsin is having the turnover number of 100. So these values, the Km and Kcat values are very much important. So these values will be derived from the Michaelis Maintence equation and Lineweaver-burk plots. And the next important equation here is Lineweaver-burk plot. And this Lineweaver-burk plot, so which is the reciprocal equation of Michaelis Menten's equation. So this is the Michaelis Menten equation V naught, which is equals to Vmax into S upon Km. So Michaelis Menten's constant plus S substrate. Here we are taking the reciprocal values of Michaelis Menten's equation. So that's why we are taking 1 by V naught. So we are taking the denominators into the numerator, and we are taking the numerator of Michaelis Menten's equation into denominator. So now the reaction will be converting like this. And from this equation, so we can make the equation in the form of a straight line equation, that is y equals to ax plus b. Here 1 by v naught value, so which is similar to y value, so y axis value, and km by v max value, so which is equals to a value, so which is a slope, and here 1 by s value, so we are taking as x-axis value, and 1 by v max value that we are taking b value, that is the intercept at so y axis. So from this equation, so we can plot Lineweaver-burk plot. So this is the Lineweaver-burk plot. Here 1 by s value that we are taking on x-axis, 1 by v value that we are taking on y-axis. So this is the intercept, that is 1 by v max value, and here so this is minus 1 by km value, and this is the slope that we are taking, that km by v max value. So here, so this plot will be very straight line. So here we can easily calculate the concentration of the substrate molecules, and also we can calculate the Vmax values from this equation. So this is the graphs which are explaining about two important equations. The first one is Michaelis Menten's equation. From this, so we can draw this plot. So here we are taking substrate on x-axis and reaction velocity V naught on y-axis. But whereas in case of Lineweaver-burk plot here, which is a reciprocal equation of Michaelis Menten's equation, that's why we are taking 1 by s value on x-axis and 1 by V naught value on y-axis. Here we are getting a linear graph in Lineweaver-burk plot, but here in Michaelis Menten's plot, here we are getting a hyperbolic plot. So this blue line, so which is indicating the enzyme reaction without any inhibitors. And here, so this green line, so which is representing non-competitive inhibitors. And if you're observing closely, here this enzyme reaction and non-competitive inhibitor, so which are having the same Km value and two different Vmax values. Here are the same observations we can also get from this Lineweaver-burk plot. Here Km values will be same and two different Vmax values, so we can get from this Lineweaver-burk plot. So that means here the enzyme reaction, so if it is shifting towards right hand side, then we can call it as a non-competitive inhibitors. That means non-competitive inhibitors will be getting the plot on right hand side, and non-competitive activators, so we'll be getting the peak at left hand side to the main peak. So this is about the peaks difference between Michaelis Menten's and also Lineweaver-burk plots. And this Lineweaver-burk plot, which are useful for identifying the different types of enzyme inhibitions. So we are having three types of enzyme inhibitions. The first one is competitive inhibition, uncompetitive inhibition, and third one is non-competitive inhibition, or it is also called to be mixed inhibition. In competitive inhibition, so here the non-inhibitor and inhibitor, so which will be attaching at the same position, that is Vmax. That means the Vmax value will be unaffected. It will be same for the inhibitor as well as as well as for the enzyme which doesn't have any inhibitors. So why? Because here competitive inhibitor, so which are acting at active site, here the inhibitor which will be competitive with the substrate, so the active site will be same for the inhibitor as well as substrate. So that's why the Vmax value will be always same, it will not be changed. But here Km value will be increased. So this is about competitive inhibition. And the second one is uncompetitive inhibition. Here Vmax values will be changed, Vmax values will be reduced, and also Km values also will be reduced. So if you take the non-competitive mixed inhibition, here the Km values will be unaffected, but Vmax values will be reduced. So by this Lineweaver-burk plot, so we can easily identify different types of enzyme inhibitions, as well as enzyme activators. So what we learn here? So let's look at the three important points once again. The first point here is, so the derivation of Michaelis Menten equation. So we derived the equation by the four important assumptions. And the second point here is the observations of Michaelis Menten's plot. So by these Michaelis Menten's plots, we can easily calculate the substrate concentrations and Vmax values and Km values. And we have to observe, we have to learn the Km and Kcat values of different enzymes. So this Kcat value, which is also called to be turnover number. So different turnover numbers and different Km values will be present for the different enzymes that we have already learned. The third point here is the creation of Lineweaver-burk plot. So this is a Lineweaver-burk plot, which is a reciprocal plot for the Michaelis Menten's plot. And this plot will be very much helpful for identifying different types of enzyme inhibitions. We have three types of enzyme inhibitions, that is competitive enzyme inhibition, non-competitive enzyme inhibition, and uncompetitive enzyme inhibition. So this is about enzyme kinetics. Thank you.